Right, folks, so let's just remember where we were at last lesson, which would have been on Thursday. Can someone just tell me what happened? You weren't here, I know, Ahmed, so you're going to need to catch up. Hopefully this first bit will give you a bit of a catch up anyway. What were we doing, folks? Jemima? Reactions of alkenes. Okay, so what do we remember? What kind of reaction will alkenes always undergo? Addition. And what is someone else? Because Jemima wants to be the talker this morning. What does addition actually mean? When we say it's an addition reaction, what are we doing? Oh, come on, help me out. What do we mean by an addition reaction? Angelina? Yeah, two molecules are going to become one. When we're talking about alkenes, what in particular happens to the alkene in an addition reaction? Ziad? Okay, more or less becomes an alkane, but it breaks the double bond. Okay, fantastic. So, what we're going to look at this morning is our second reaction mechanism. Okay, and when I say reaction mechanism, that should make your ears prick up and think, this is going to be really important for us. Okay, so it's called, I'll write it up. The nice long word there. It's addition. We know alkenes undergo addition reactions, but the new word there is electrophilic. So it's quite important actually to think what that word means. Okay? Particularly the end of this word. Okay? Well, electro probably means what in chemistry? Electrons. Exactly. Okay? So something about electrons, and then this bit, philic or phile, has a meaning as well. You might have heard other words that have phile on the end of them, P-H-I-L-E. Leanne? Kind of like attractive, yeah. Go on, what were you going to say?
Like, they give away electrons?
Not necessarily.
No.
They don't necessarily give away electrons. But phile, really, if I just take out the IC and make it electrophile, if something has got phile on the end of it, it means it likes it. Okay? Or you like it. So you can be, for example, in just using the English language, you can be an Anglophile. I don't know why you'd be one of those, but an Anglophile is someone that likes English people or English culture. Don't know why you'd want to be that. Same thing, you could be a Francophile and like French people and French culture and so on. Okay. What was the other meaning? The other scientific meaning you might have come across, biologists, you might know this, okay? Because there's also the opposite of phile, which is phobic. What does phobic mean? Scared of, exactly, to have a fear of. So you can be, for example, not in science, you can be, what was that one? You can be agoraphobic. What is an agoraphobe? People that are scared of open spaces, exactly, are agoraphobes. In biology, you can be hydrophobic, okay, which is what? You don't like water, exactly, okay? So a hydrophobe doesn't like water. But if you're a hydrophile, then you really love water, okay? And you might have learnt already in biology, I don't know, have you done like the cell membranes and fluid mosaics and things like that, okay? So the bits that make up the membrane, they have a hydrophilic end and a hydrophobic end. And then the hydrophobic ends join together and you get the cell surface membrane. Check out my biology knowledge this morning. Yeah? So anyway, electrophiles love electrons. That is the meaning of the words, all right? We got there in the end. So there we go. So electrophile means electron loving. Think about this though in a chemical sense for a second, folks. what do we know about electrons? What is an electron? Yeah, it's a subatomic particle that is negative. Okay, so to be an electrophile, what do you probably need to be? Positive, exactly. Okay, you need to be positive in some way. That might be a completely positive charge, or it could just be a partial positive charge. Okay, how do we represent partial positive charges in chemistry? Yeah, delta plus, exactly. Okay, so electrophiles. Cool. So electrophiles usually have a positive or partially positive, delta positive charge on them. Okay. What was the reaction that we were looking at last lesson? We did it with the practical. What did we react together? Okay, so we did an alkane and an alkene with bromine. Okay. Which one did actually react? Cyclohexene. Okay, it was only the alkene that reacted, all right? So we're going to look at that reaction as a mechanism and actually see what chemists believe actually happens in that reaction, okay? And it's not actually that tough, to be honest with you, okay? But there are things to remember. And now, when we have our mechanisms, we're going to start using arrows and all types of things you've not seen before, okay? There are different ways to go about remembering this. Okay, lots of you are probably just going to try and put it all into your memory in one go. Okay, that's quite difficult to do. We need to break it up into little steps. Okay, and try to understand it more than just memorize it. Okay, so we're going to start off with our two reactants. I'll make the alkene nice and simple though. We'll start off with ethene, okay? C2H4. What was it reacting with? What am I going to react it with? Huh?
HBr.
Not HBr. Just bromine, yeah. It was bromine water, but we're worried about the bromine doing the reacting, okay? I'm going to put the bromine here. Okay? The bromine molecule itself, is that... does that have delta positive and delta negative parts of it, a bromine molecule? No. Why not? It's really electronegative bromine. Why does it not have delta positive and delta negative parts?
I don't think it has sufficient polarizing power to kind of break down into, or no?
Not quite, no. I can see why you say about polarizing power, but just try and think about electronegativity, okay, and what you know about electronegativity. Because bromine is electronegative, but it's a bromine molecule.
Both bromine atoms have like the same electronegativity, so they pull with the same power. So basically, like it cancels out.
Exactly. So they're both electronegative, but they're both equally electronegative. So that pull of electrons cancels each other out. Okay. So there is no polarity on a bromine molecule. Okay. But we need to make from bromine. Well, we need to come up with this. Come up with an electrophile. Okay. The double bond here. What does the double bond have lots of? Electrons. Okay. Interesting. So if there's lots of electrons here, and this bromine comes close to it, what's going to happen to the electrons that are on this bromine? There are lots of electrons here. What's going to happen to the electrons here? Ziad. Okay, it will repel the electrons downwards, okay, away from this area that's got loads and loads of electrons in it, okay? So actually, as soon as it comes near to this, it becomes polar, this bromine molecule, okay? And if electrons are moving this way, down the molecule, what does that mean here? I can put a delta here, but which one? Am I going to put a delta positive or a delta negative? Positive, exactly, okay? The electrons are being moved down, so there's less electrons here, more electrons here. So I'm going to put in my partial charges. Delta positive and delta negative. There we go, okay? Wow, now suddenly you've got something that's positive that can be an electrophile. Okay? Just let you catch up with this and absorb for a second. You got a question there?
Yeah. So would all elements and atoms be considered electrophile fields? Because if you think about it, it always could kind of force the electrons down to the other side when it comes out. Or is it just
It won't be able to do it to everything, to be honest with you. But anything that an alkene can react with needs to be an electrophile. Okay? To undergo that addition reaction, it needs to be an electrophile. Where am I looking for here? Oh, yeah. Cool. Okay, so you'd think, wouldn't you, now that we're talking about this, we've got an electrophile, you kind of think, oh, it's going to attack that. Yeah? Which in a way it does. But actually, the way we think about this is that we're always thinking about how electrons move. Okay? And we're going to show arrows, what we in chemistry we call them curly arrows, okay, to show how electrons move. Alright? So now I've got the delta positive here. Okay? Effectively this double bond can attack the positive. And we show that nice and easily with little curly arrow from here to here. Okay, curly arrows in our mechanisms, they always come from a bond or they come from a lone pair of electrons. Okay, in this case they come from the bond. So, double bond attacks on the positive. At the same time, from the bond here, okay, the electrons, there's more electrons coming in, it's going to push all the electrons all the way down, it's going to break the bonds. To show a bond breaking, again, I'm going to put in a curly arrow, okay, from a bond towards an atom, okay. And that's our first step in electrophilic addition. So we've got the delta positive, delta negative, curly arrow from the double bond to the positive bromine, bond breaking towards the delta negative bromine. Okay? It's going to be the same pattern all the time. Alright? So, step 2, we want to show what's been made by what happens here. Okay? So this attack here, what do you think happens to the double bonds when this attack happens there? Clear? It breaks, exactly. So we're going to have our intermediate has just got a single bond. Okay? I'm going to put in the H's that were already there. None of them are broken off. Just going to put them in like that. Okay? Now when that bond broke and the electrons moved, it was able to form a bond with the bromine. And so I'm going to put one bromine in. Like this. Okay, but I've only joined one bromine on so far. So what I'm left with is this intermediate step, which is not really a complete molecule, but it is, or it does have, a positive charge on it. Okay? Because look, this was delta positive. Okay, the electrons moved, this bond broke. Okay? This ended up being positive, and now this whole thing is positive. Okay? It's a... Here we go, I'm going to put a positive in there. The name for that intermediate, well, it's an ion. If it's a positive ion, what would we call it? Cation, exactly. Okay? This is, to give it its full name, it's a carbocation. Not a carbocation, definitely not, but it's a carbocation.
So the double bond, carbon double bond attacking the bromine leads to the bond between the two bromine atoms.
Breaking, exactly, yes. So that step shows that the bond was broken. Yeah? I'm also left with something else from here. What was I left with as well? Go on out, I think.
Bromide ion.
A bromide ion. Yeah? Okay. That's what I was left with. This bond broke, all the electrons came down to it, so it ends up being fully negative. And so I've got Br minus. I'm going to show it with a lone pair on it as well. Okay. Go on, Ahmed.
So you know you said the carbocation is positive and the bromide ion is negative. Why doesn't it just like?
It's about to.
Oh, okay.
Is the answer to that. Okay. So I guess we could show it like that. Yeah. Go. So the last step, well, we want to show, I think some of you have actually worked out what happens. Okay? What do you think is going to happen to that bromide ion now? Ziad? Exactly, it's going to, well, it's already attracted into here, so it's going to form a bond here. Okay? Now, I want to show an arrow with how the electrons move. So, maybe you can work out already which direction will my arrow go. James?
Well, you said it only goes from bonds or lone pairs.
Yep.
So it goes from the two dots to the carbon.
Exactly. So it can only go from a bond or from a lone pair. So it needs to go from the lone pair to the carbon. Okay? And in the final step, we just show what the product is. And we already know that from last lesson anyway. We've got our, what did we call that? We had a name for it last lesson, didn't we? Pranesh, what did we call it?
1,2-dibromoethane.
Exactly. 1,2-dibromoethane. Okay. And that's going to be the same kind of pattern all the time. Now we need to know the mechanism for that reaction. I'm just going to leave it on the board for a sec so you can kind of catch up and ask any questions of each other that you want for a minute or two. And I'm going to get you to do something, okay? This is going to be an example for you folks to work on now. Taking the original one off. Okay? This is the only other example of the mechanism that we need to be able to do. Okay? It's not with bromine. It's with HBr instead. Okay? Now, first off though, just thinking about this, what do we already know about this molecule? What's different about this compared to bromine? Okay, the H is already delta positive, and this is delta negative. Okay, so you don't need to induce a dipole. The dipole is already there. But what I want you to do over the next few minutes is just to see if you can apply what you already know about the mechanism to draw out exactly the same thing. Okay, and see what you end up with at the end. See what the product will be at the end. Okay.
UPR is separate from
Right, folks. So, I think I've looked at most of your work. Okay, and it seems pretty good to me what you've done. Okay, you should have. In fact, I'm going to ask you as we go. What's the first thing you would put into this mechanism? I'm going to pick on people because you're not being very forthcoming this morning. Gabby, what would be the first thing you would add to this?
like as the product.
No, just on this part of the diagram, what would you add first?
I would add the delta positive.
Okay, so delta positive on the H, and then what would I add there? Yeah, you did say that. Sorry, I didn't quite hear you, that's all. Okay, so delta positive and delta negative. That would be the first thing to add, definitely. Okay, always follow it through in a logical order. Maria, what would you do next?
So you draw an arrow going off the double bonding between the carbons.
Yeah.
To the hydrogen.
Exactly, so I want an arrow going from the double bond towards the hydrogen. Perfect, the attack. Okay, who's next? Pranesh, what am I going to do next?
Write it out. Guess the product.
Oh,
You draw another arrow to the bromine.
okay, an arrow to the bromine. Where's it coming from?
From the bond.
Which bond?
The bond between hydrogen and bromine.
Exactly, the bond between the hydrogen and the bromine. Okay, so I want an arrow from there. And I'm really picky about this. Okay, examiners can be really picky about it. Your arrow literally touches the bond. Okay, make sure it actually touches it. Be neat about it. All right, that one doesn't look particularly neat, but do it as I suggest. Then we're going to move on to the next step. I'll help you out with the chain. I'll break up the double bonds. We need a H there. We need two H's there. We need three H's there. Okay. That's just exactly the same. I've just broken the double bond. But what am I going to add on and where? What do I need to add on? Leanne? A bromine?
A hydrogen,
A hydrogen. Where did you put the hydrogen?
the one beside them. So yeah, the middle. Yeah.
You put the hydrogen there. Okay. I'm going to put it here, if that's okay. And I'm going to come back to why I put it there in just a second, okay? Looking around, actually, most people did actually put the hydrogen there and not there. Yeah? I'd say the majority of people put it there. And I'll come back to why that is important in a second, okay? What else am I going to add to who I've not spoken to yet? Abdullah? Whereabouts? Okay, I want a positive at the middle carbon, okay? James, what am I going to add next? A BR with a lone pair, there we go, that will do there. Did I need anything else with that BR? Something else beforehand that's important. Maybe you've got it on your diagram and you can't quite see it on mine. What the difference is. Not just slightly negative, fully negative. Okay, it needs to be a bromide ion, Br minus. Okay, so that's important there. Did you have that on your diagram? No. Important to add in that case. And then you're right. I'll give you that squiggly line, curly arrow, please. Not just a squiggly line. Curly arrow to the C. Okay, and then final product. I can draw that. You've given me everything I need now. Put a H there, BR there. Okay, that's the product. Just when it came to naming that, a couple of people, in fact about 3 people, had a double number with this. They said 2,2-bromopropane. Okay? Just be careful on the naming. If you've got 2 numbers, then you must have 2 things. Okay? This is just 1 bromine atom, so it needs to be just 2-bromopropane. Okay? And like I said, Leanne, to you, I did it as 2-bromopropane for a very, very good reason, and one that I didn't actually tell anyone about beforehand. I wanted to see how many people would come up with either 1 bromo or 2 bromo. Okay? This is a good learning point, actually. The major product from this reaction, the majority of the bromopropanes will be 2-bromopropane. Only a very small amount will end up being 1 bromopropane. You might think to yourself, I don't know if you're actually even thinking about this, you're like, well, surely it's kind of a 50-50 chance. Sometimes they go on to this side, sometimes they go on to that side. It's not quite a 50-50 chance. I need to tell you why. Okay? I'm going to rub this off and have a little chat about this. You should all have that hopefully in your notes because you did it perfectly anyway. I saw some amazing curly arrows in what we did. So, is that right? We'll talk about it like this. So, what am I trying to get at here? Oh yeah, so when this reaction with HBr, there was 2 possibilities, okay? Because the alkene we're reacting with is not symmetrical, then it's possible that the bromine can go either side of the double bond, and we end up with 2 different products, okay? In this case, we worked it out because different people drew different things. So we had 1 bromopropane or 2 bromopropane. The reason though that this 2 bromopropane is the major product is because of our intermediate. If I show you the 2 different intermediates, you might be able to see the difference. So that's the intermediate that will lead to 2 bromopropane. And that's the intermediate that will lead to 1 bromopropane. Now we'll talk about this more when we do the next set of compounds, which are alcohols. But this one over here, this is called a primary carbocation. This one is a secondary carbocation. I'll write it in there. You notice some of these words and phrases start to get very long now. A primary carbocation and a secondary carbocation. The primary, the positive charge, is right at the end of the chain. In the secondary, it's in the middle of the chain. We can also go one further up as well, and we'll look at that when we do alcohols. We can have a tertiary as well. Go on. Can you see the difference between the two first, Leanne?
Because this one's more stable.
That's a very good answer. Okay? So the reason that this is going to end up being the major product, so this carbocation, Bismuth and Angie, is far more stable than this one. So this one is much more likely to form than this one. Okay? And the reason that it's more stable, it's got more area for the positive charge to kind of spread around it. Over here, the positive has got to be kind of concentrated almost on the end of the chain. Here, it can sort of spread out a little bit. Okay, so this is much more stable, and so 2-bromopropane becomes our major product. Yes, Ian?
So isn't the primary?
So
The primary should be the other one, the one after that.
this is called primary because it's at the end. This is called secondary because the positive is in kind of in the middle of the chain. But it's the secondary that is more stable. Okay? And so the secondary leads to 2-bromopropane, which is the major product. Alright? So, you right, Leah? Did I just give you too much information? Or is it too hot in here? It is really hot, isn't it? I know. Apparently they've adjusted the AC for tomorrow. So, hang on a second. I'll just write a bit in here and then I'll open the door. Alright? So, nice long words in my sentence. So the secondary carbocation is more stable. So 2-bromopropane is the major product. I wonder if I can give you a little exercise on that. Alrighty, so okay then, so we've got about 10 minutes left. I know I've probably blown your head up with all of the extra knowledge today, but A and B up here, what I want you to think about, so we've got butanene and HBr, plus that compound, that's actually methylpropene, plus HBr. I want you to try and work out, you might have to do it by drawing a mechanism, you could probably do it without as well, but I want you to work out which one, because there's two options, what one you think would be the major product, okay? And give it a name as well. See what you can come up with, okay? So it's using this idea up here. Way too hot. You know it's hot when Mr. Barfoot is literally like sat outside his classroom. Angie.
For these ones, is it the propane?
Yeah.
Look, it says